Now in this lecture, we are going to look at why we need to drop constants and non-dominant terms in big O. Dropping constants and non-dominant terms means that we can easily eliminate some values from asymptotic analysis. So this means that when we drop constants, we can write O to n as On. So in this case, we are dropping 2 from here and writing On like this. So expressing O to n like On is kind of similar. So the constant over here does not play an important role. Now when we are dropping non-dominant terms, so for example, On squared plus On can be written as On squared because in this case On squared takes much time than the On, so that's why we are removing the non-dominant terms. So in this case, non-dominant term is On. Now for example, for this one we know that, O log n performs better than On, so that's why we can remove it from here. We can write it On. Now for example, if we have some complex expression like this, so in this case we can write is O 2 to the power of n, because in this case this is the biggest value in this expression over here. Now you might be interested why we are removing this. So the first reason is it's possible that On code is faster than O1 code for specific inputs. So big O just describes the rate of increase. So for this reason we drop constants, and which means that O to n is actually On because we are eliminating the external factors from our expressions. Now we know that different computers with different architecture have different constant factors. A faster computer might be able to access memory faster than a slower computer. So faster computer will have a lower constant factor for memory access than the slower computers. But however, we are just interested in the algorithm, not the hardware. So the constant terms in asymptotic analysis expresses the computer hardware. So we don't need to analyze the computer hardware because here we are interested in the algorithm when we are doing asymptotic analysis. So we ignore such constant terms from our expressions. So also slightly different algorithms with same basic idea and computational complexity might have slightly different constants. For example, if we have two expressions like this, so if we write these two expressions inside loop, it's possible that if the multiplication is slower than the subtraction in a computer, so it's possible that this first expression will be faster than the second one, because in the second one we are doing 2 multiplication, in the first one we are doing only 1 multiplication. First we are doing subtraction, then we are doing multiplication. So in the computer the multiplication is slower, that's why it will perform this one. So for this reason we need to ignore non-dominant terms and constant. So the last reason is, as n approaches to infinity, the constant factors are not really a big deal. Constant factors are very small in the arbitrarily large n. So if our n is quite big, so we don't need to worry about infinity. So for example, 2n or n, both of them approach to infinity, express the same meaning. That's why constant factors are not really a big deal in this case. So all in all, in asymptotic analysis, we ignore constant factors because it removes a lot of noise from hardware and small change in algorithm. And these things are not important for analysis. And this makes our algorithm easier to compare. So when we remove the non-dominant terms and constants from our expression, so our expression becomes simpler, and it's easy to compare asymptotic analysis with the simpler expression rather than complex expression. So in this lecture, I explained why we need to drop constants and non-dominant terms from big O. So hopefully everything is clear about this. Now with this, we have come to the end of this lecture. So see you in the next lecture.